Okay, let us continue our discussion on step growth polymerization. Now, before we come to this lecture's topic, let us just recapitulate what we have learned in last lecture. In last lecture, we have completed the kinetics of step polymerization, and we have seen what is, after looking at the kinetic expression, we have convinced that for a polymer chemist life is little difficult compared to organic chemist if we talk about the utility of conversion. For a organic chemist who deals with the small molecules, a 98% conversion may be good enough, but for a polymer chemist 98% conversion might give you only a degrees of polymerization of 50. So, if you have to improve or increase their molecular weight, you have to take your reaction for longer and longer, which makes it more difficult for a polymer chemist. We also in that kinetic polymerization proved the theory of equal reactivity of functional group. Then we went on and studied how the degrees of polymerization would vary with equilibrium constant in a closed system, and we found that the importance of equilibrium constant in that case, if you want to build high molecular weight in a closed system without removing the condensate out of the polymerization medium, then your K value, the value of the equilibrium constant, has to be quite high to build a decent enough molecular weight, that is why it is never practiced. The step polymerization is never practiced in a closed system. It is always done where you take out the condensate from the reaction medium, and in continuation we found that we understood that it is not always possible to take out 100% of the condensate which is getting produced in the reaction. So, we found the quantitative relations between the amount of condensate present at the end of the reaction with the degrees of polymerization, in that along with its relations with equilibrium constant, and we have seen that unless we have a quite high value of equilibrium constant, we have to go down the residual value of the condensate to a very low level to build a high enough molecular weight. If we cannot take out the condensate from the reaction medium such a high level, so that the residual level of that condensate in the polymerization medium is low for whatever reason, then we have to design the monomer such a way that the equilibrium constant is pushed up or the reactivity increases. In that case, we can afford to leave more amount of condensate molecules in the polymerization medium in order to build high enough molecular weight. We also studied what are the strategies for controlling molecular weight in a step polymerization, and the two recommended strategies are either one should use a slight excess of one of the two bifunctional monomer, or a slight amount of a chain stopper, which is nothing but a monofunctional group. Now, what we plan to study in this lecture is continuation of the strategies, and now we in this lecture we quantify the relation, that means how much excess, we use the term slight excess. So, how much excess you should use for your target molecular weight, or how much monofunctional monomer you should add for a target molecular weight. And then we will also learn the molecular weight distribution among the chains which are formed in step polymerization, and then calculate AMW and polydispersity index, and then at the end we will compare between cyclization and linear polymerization. So, let us begin with where we left in the last lecture. Now, we know that degrees of polymerization, average degrees of polymerization is given by the number of monomer group or functional groups at the beginning, number of molecules at the beginning, and by the number of groups at time t. Now, let us consider a case where we have this system A and B with slight excess of BB. This is present in slight excess. So, we define a ratio which is imbalance ratio R, which is the moles of A number of BB. Now, R is defined in such a way that it always less than equals to 1, it will never be more than 1. So, the monomer which is present, this should come as a denominator, so that R is always less than equals to 1. So, what you need to find the molecular weight or degrees of polymerization, we have to find N0 and N. Now, if Na is the number of functional group groups present at the beginning, groups of A present at the beginning at t is equal to 0, and Nb is the number of functional groups of B present at t is equal to 0. So, what are the total number of A molecule at t is equal to 0? Total number of A molecules is Na by 2, because each molecule have 2 functional group, and total number of Bb molecule is given by Nb by 2. Now, Nb is R is Na by Nb. So, Nb is Na by R 1 over 2. So, total molecules at the beginning, total number of molecules at t is equal to 0 or N0, which is N0, is Na by 2 number of A molecules plus number of Bb molecules Na by I 1 by 2, which gives plus 1 by R. Okay, clear? Now, we have to find out this. We know N0 now, we have to find out N, which is the number of molecules at time t at some reaction. Now, if conversion is P, so number of A molecules reacted, A functional group reacted is P into Na. So, number of B group reacted, again each A will react with one B. So, number of B group will be same as number of A group. Okay. Is it clear? Because conversion is P, conversion is defined the fraction of functional group as reacted. In this case, A present in a smaller amount. So, we consider A. So, number of A groups reacted is fraction in the total present initially, P into P multiplied by Na. Now, each A group will react with one B group. So, total number of B groups will react also this. So, how many of A is remaining? So, remaining number of A group is earlier what Na, now it is Na into P, which gives Na 1 minus P. How many B groups remaining? Earlier was Nb minus P Na. Again NB is Na by R P Na, which gives us Na 1 by R minus P. So, this is the number of A groups remaining, and this is the number of B groups remaining. So, total number of functional groups remaining unreacted is sum of these two. So, total number of functional groups unreacted is summation of these two. I can take both together, 1 minus P plus 1 by R minus P, which gives us Na 1 plus 1 by R minus 2 P. Now, these are the number of functional groups unreacted. So, how many molecules will be unreacted left over? Each molecules have 2 functional groups at 2 ends. So, how many of number of groups, number of molecules present now? So, N, which is the number of molecules left over, each molecules which is left over now in the polymerization medium, which have 2 functional groups. So, if you divide the total number of functional groups unreacted by 2, it will give you the number of molecules left. So, N is Na by 2 1 plus 1 by R minus 2 P. So, x n bar is n 0 by n, which means Na by 2 1 plus 1 by R divided by Na by 2 1 plus 1 R minus 2 P, which leads to 1 plus R minus 2 R P. Okay. So, that is the expression which relates the number average molecular weight with R, which is the ratio of the moles of 2 bifunctional monomer present in the system at the beginning, where R is defined such a way that it is always less than equals to 1, and P is the conversion, which is defined as the fraction of the functional groups which present in a smaller quantity as reacted. If in this case A is the functional groups present in smaller quantity, the fraction of A group which has reacted is defined as the conversion. Okay. Now, so if I plot this, how does it look? Okay. So, it will look something like this, where this is the direction of P. P is 1 in this case, and the other curves are for lower P's. Okay, which means for a given R, if you take any of the R here, as you increase P, molecular weight goes up, which is expected, and for a given P, for any of this, if you consider any of this curve, as you increase R, if you go close to stoichiometric, you will increase the molecular weight. Okay. So, the ideal scenario of working is somewhere here, where you are your R is close to 1 and P is close to 1. That will give you the highest molecular weight you can achieve. If you off in any of these two factors, if your R is somewhere here, then no matter what is your conversion level, you cannot reach high molecular weight, you will stop here. Okay. Same as if your P is low, so like this curve, no matter what is your R, you can only reach up to this level. So, for a successful step polymerization, successful by mean by successful I mean to build a high molecular weight, you have to have a condition where R is close to 1, so as P is 1. Now, if you have some molecular weight in target, you can use this formula and you can complete the reaction in such a way. Now, R is the ratio of the functional group of the two bifunctional monomers. So, you need to know the concentration of each monomers very well. Now, how do you know? You can only know the concentration of each or the moles of each of the monomers and the functional group if they are pure enough. If there are impurities present in your monomers, then you don't know, you are not sure what is the actual mole fraction or mole of the functional groups, which restricts that you must have very pure monomer in order to get a successful step polymers. Okay. And also same time your reactor should be high enough, so that you can take out your condensate such extreme way that you can push your conversion up to P. Now, it is sometimes it is difficult to quantify the P, it is difficult to quantify P, because you cannot take out the alicate during the reaction and determine the functional group present, and so by which you can determine the conversion. So, what is typically done? You do your reaction best possible way, and that is the limitation. So, that is the maximum you can go, and if your reaction system is good, your reactor is good, your vacuum system is good, then you can hope that you will be your P would be close to 1. Then you can control your molecular weight, you can target your molecular weight by adjusting the ratio between two monomers or the fixing a value of R. If you consider P as 1, if you makes your P is 1, then x n would be 1 plus R, 1 minus R. Okay. This is typically done. You do your reaction best possible way, at best you can do, and hope that P is close to 1, and you can choose R at the beginning, so that you can target x n accordingly. And there is another case where R is 1, x n would give us back the original Carothers equation, where we started with 1:1 ratio of the two bifunctional groups. Now, there is a second strategy we discussed, type 2, that was earlier was type 1, type 2 where we said that we can control the molecular weight by adding a monofunctional group, monofunctional compound or monomer substance, whatever. Now, let us take a situation where we have say a B type molecules plus some excess B or AAA type, PP type plus some excess B. So, you can use the expression which we will get it for this simple any of this simple scenario where you have AB or AA BB in 1:1 plus these things plus some monofunctional monomer which is chain stopper. Now, in that case also you can use the same expression which we got in the last page. In that case also you can use the same expression, only difference is that in this case R is defined as Na plus Nb plus 2 Nb dash. Okay. The same expression can be used for this scenario as well. So, what is scenario where you have either A or B or 1:1 AB plus some excess B. In this case Nb dash is the moles of number of moles of this molecule monofunctional group having B. You might question what is the origin of these two. Now, that is because this has same effect as a excess BB. This has same effect of a excess presence of a excess bifunctional monomer. Now, to equate these two is added. Okay, to compensate these two is added. So, now with this formula you can use or you can target a molecular weight. You can start with a 1:1 A and B, these two monomer A and BB, and then add slight amount of this monofunctional group and target a certain molecular weight using this expression where R is defined as this. Okay. Now, what is the advantage of this monofunctional group? If you remember that in this case using monofunctional group the ends are capped with non-functional group, and when you use the other strategy, the type 1 where you have one of these groups excess, you still has virtually dead polymer, but there you have same functional group present in the both the sides. When you use this first strategy, you have same functional group present in both the sides, so that they do not interact with each other, they react with each other, but you still have functional groups. So, in case if there is a in future when you take this polymer for other reaction, if there are some impurities analogically present which might react with this functional group, you might land up in a problem scenario. Whereas, if you have a monofunctional encapper or chain stopper, then the ends are capped with non-functional groups. So, it will not react. So, that is the only advantage in this case, but in this disadvantage that you have to have a extra molecule in the reaction medium. Okay. We will move to the next topic of molecular weight distribution. Now, you know that the product of a polymerization is a mixture of different polymers of different chain lengths. So, in any polymerization reaction, you at the end of the reaction you have a distribution which contains several molecular weights. Now, in a step polymers, how the distribution looks, we will try to get some information, some prediction from statistics. Okay. See whether we can estimate, we can predict what would be the molecular weight distribution, both number average and weight average, weight fraction distribution of the molecules present. Now, we have to consider, or we have to find what is the number fraction or say probability, what is the of finding a chain with x mar, x structural units. If we can find the probability of all x, all x's, all values for x, then we can surely get the distribution. So, is for generalize, let us try to find out what is the probability of finding a chain in the reaction medium with x mar. Now, if you consider a reaction of A plus BB type or say AB type and consider this is present in 1:1. Now, this following statistics was first done by Flory. So, this distribution we will get is known as Flory distribution. Now, how do you get this probability? In x mar means x n is x. X mar a chain which has x number of structural units, which means degrees of polymer of is x. Now, how many A molecules there? In a x mar, the number of A groups, A structure x structure, so number of A groups will be also x. Okay. X is the number of structural units. So, number of A groups also will be x. Now, out of this x number of A groups, 1 is at the end unreacted, and x minus 1 have reacted to form linkages. So, if you have x mar out of which 1 is the end which is free and x minus 1 is the number of A functional groups has which is reacted. Now, what is the probability of finding one free A group? If P is the conversion, probability of one free A group is 1 minus P. Free means unreacted. Probability of one A group reacted is P. P is the conversion. So, what is the probability of 2 A group reacted? P into P or P square. 3 A group reacted, P cube. So, in x mar we have x minus 1 A group which is reacted. So, in x minus 1 x mar, the probability of x minus 1 A groups reacted is P to the power x minus 1. So, in case of x mar which has one free A group and x minus 1 A groups which are reacted, the probability of finding such x mar is given by 1 minus P, the product of these two probabilities x minus 1. Now, what does it mean probability of finding a chain which has x structural units? which is nothing but the mole fraction, mole or number fraction of x mol, which is say n x 1 by p, p to the power x minus 1. This is your mole fraction. So, again I write mole fraction of x mar is given by 1 minus p, p to the power x minus 1. Now, what is this mole fraction? Is the number of molecules having n mr. So, n x is the number of molecules having n x mr, x structural units by total number of molecules present at that time. So, 1 minus p, p to the power x minus 1. Now, what is n? N is the total number of molecules present at time t, which is given by the total number of molecule minus p n 0 as earlier. So, n 0 1 minus p, where n 0 is the number of monomers at the beginning. So, n x will be given by n 0 1 minus p square p x minus 1. So, this is the number of molecules present which have x mar, x number of x mar, which means number of molecules or chains present at any time having x number of structural units. How does it look, this distribution? Let us draw it again, next page. This is of the order of p. So, if this is the direction of p, which means at lower, this is the lowest p, this is the intermediate p, and this is the highest p, which means at lowest p your polymer mixture has maximum number of molecules having low x, that means low number of functional group. If you have an intermediate conversion, in that case also the maximum number of group present or maximum number of molecules present are the molecules having lower number of structural units in the chain. If you increase the conversion further, then also the maximum of the number of chains having small number of functional groups or small number of structural units are maximum, but this difference comes down as we increase P. So, what does it mean that in case of step polymerization at any point of time, whether it is a small conversion or high conversion, what is the number of molecules which is present in maximum are the monomers, because monomers has the least number of structural units. If you look at the distribution, the maximum in on the left hand side, which is the minimum of x, that means these are the monomer. So, at any conversion region, whether it is a small low conversion, medium conversion or high conversion, the reaction medium will have in number fraction, in number, not the weight, in number wise maximum number of monomer present. Now, the number of monomers will decrease as the conversion goes up, but even at very high concentration there are significant number of monomers present in the reaction. So, if you take a monomer a polymerization mixture at the end of the things, maximum number will be present are the monomers, then dimers, then trimers and so on. Okay. So, the real polymers would be in the smallest number present in the reaction medium. So, in case of numbers, but numbers are not always very significant, weights are more significant than numbers. So, how we will look at how the weight fraction is distributed, how the weight fraction of this individual chains varies with x, which is the number of monomer present. So, weight fraction, how do you get weight fraction? Weight fraction of x mol is the weight of all molecules of x mol divided by total weight of the mixture. If Nx is the number of molecules having x structural units, so Nx is the number multiplied by x, which is the number of structural unit present in one molecule. X is the number of structural units present in one molecule, and Nx is number of such molecules. So, total weight Nx in x and M average is the molecular weight of the structural units. So, this is the molecular structural units, this is the number of structural units present in one chain, and this is the number of such chains, and if you can sum, total weight is sum up of all such x mar, so all values of x. So, we can get Nx by x, Nx a total, this summation for all x's would give you the N0 total number of molecules. Okay, and Nx by N0 we have seen earlier, we can put that value and we can get this expression. So, that is your weight fraction. So, weight fraction is given by this number, this expression, whereas number fraction was given by this was N0 here. Now, how a plot will look like? If I plot here, so weight fraction of x mar, it will be something like this. because if you plot the weight fraction, as you can see from this distribution, that unlike in case of number fraction, you have always the maximum number was the lowest x, the chains having lowest x and monomer being the least x, okay, 1 x. In this case, there is a distribution with maximum, there is maximum, and this maximum around comes about the x in bar, number of average. This x is where the maximum comes, it is about the x n bar, and this is again with increasing p. So, this is the least p, this is your intermediate p, and this is your highest p. Okay. So, as expected, with increasing p you have x also increases, the molecular weight increases, but if you plot weight fraction, you can see it is not the monomers which are, or the dimer trimer which are present in maximum number. What is present in the maximum? It corresponds to the polymer chains which is having average degrees of polymers. Okay. So, the weight if you take all the chains and plot the weight fraction, you will find maximum where x is equals to or near to the average degrees of polymerization. But in case of number, if you talk number fraction, it is the lower monomer, dimer, trimer, they are present in the maximum number. Okay. But it is weight which matters most, not the number. In terms of polymer properties, the weight would be more, because monomers or dimers which are present, they will not significantly contribute any polymer properties, is the weight which will contribute more in terms of polymer properties. Okay. So, if you want to get the m in bar and number average molecular weight and weight average molecular weight from this distribution, how will you get it? We know the weight number fraction and weight fraction, and we also know the expression for m n and m w. M n we know x n bar multiplied by average molecular weight of the structural units, and x n bar is mole fraction multiplied by the number. So, which is given by x n 0 1 minus p square p to the power x minus 1 sum over x, and if you do this maths, you will end up 1 minus p. M w is x w bar, m average, x w bar is weight fraction multiplied by, here is number fraction, it is weight fraction. So, you x square 1 minus p square p x minus 1, and if you solve this, we will get x bar is 1 plus p 1 minus p. So, what is the polydispersity index, which is given by m w bar by m n bar, same as x w bar x n bar is 1 plus p 1 minus p divided by 1 minus p, which is given by 1 plus p. So, p d I is 1 plus p for step polymerization. This is very important because it lands up, in most cases PDI is 2. Why is it so? Now, as we have seen, I understood in lectures, last lecture and previous lectures, that to make a high enough molecular weight which is useful for application, P has to be very close to 1. Now, if P is close to 1, PDI is almost every case is close to 2. Okay. So, you cannot make a step polymers of high molecular weight where PDI is narrow 1, 1.2, 1.3. That is not possible, because remember what you have told, that to make a high enough molecular weight you have to be having R is equal to 1, close to 1, so as P is close to 1. If you are off P to a lower level, then no matter what is your R, no matter whatever is R, whether R is 1, still you get low molecular weights. So, if you have high molecular weight polymer, nobody can claim that he has a very narrow distribution of say 1.2, 1.3, 1.5. That is not possible. Whenever you make high molecular weight by step polymerization, you are going to get up a polydispersity of close to 2. So, without knowing both the molecular weights Mn bar, Mn, if you know only one of them and you have given the structures, from structure if you know that this is made by step polymerization, if you are given only one of them, so if you are given Mn as 10,000 and a polymer is supplied to you, given you know the structure, and from the structure if you know that this is made by step polymers, then you know Mn is 10,000, that means you know also P, which is close to 1, say in this case say 98% or something, and you also know PDI, which is close to 2. So, you know MW bar is close to 20,000. So, from a single data of Mn and the structure you know all others, P is say close to 1, in this case exactly to be exactly it is 98%, but for all purpose we can consider P is 1 and PDI is close to 2 and MW is close to 20,000. Okay. So, this should be clear. Now, we have seen in last page that PDI is 1 plus P, which is always close to 2, or if the molecular weight is lower, it would be less than 2. It can never be more than 2, because P cannot be more than 1 any time, at any point of P cannot be more than 1. So, P is very close to 2, at most if your polymer molecular weight is low, it can be little lower than 2, it can never be more than 2. But in practice, most of the industrial polymers, at the end of the polymers, if you measure the molecular weight distribution, you find it is found that PDI is slightly more than 2, not much, say 2.2, 2.5, something like that. So, theoretically we have seen that it can never be 2 by more than 2, but in practice we find that after end of the polymerization reaction, if you do experimentally find what is the molecular distribution, you find that it is slightly over 2. So, how is it possible? It can only possible if there are side reaction which are producing smaller molecules in excess. Now, if you any distribution have more smaller molecules than expected, then MW and Mn both will come down, but as you know that smaller molecules affect more Mn than Mw. So, the percentage drop in Mn because of presence of non-polymeric small molecules, the effect on Mn will be more than Mn. So, Mn will be dropping more compared to Mw. So, your PDI will go down, that means it will be more broader. Okay. How can what are the types of side reaction we have? One major side reaction is, which is present in most of the polymerization step polymerization reaction, is cyclization. Okay. Now, you understood why we are bringing this concept of cyclization. Now, as you seen that as I said that most of the case PDI of a polymer after reaction found to be little over 2 in practice. That means, there are side products which are small molecular in nature, which affects Mn more than Mw, which means the Mw by Mn goes up. So, PDI goes up little over 2. Now, how can cyclization product, if you consider the molecules, they are both functional in both the sides. So, if you they can react intermolecularly and make a cyclic product. So, if I talk about a amino acid, it can form a cyclic product plus H2O. If you have a hydroxy acid, then it can form a cyclic product like the monomer itself. These are the intramolecular reaction in the monomers of AB type. If you have monomers like AA type or BB type, then you have the intramolecular reaction cyclization. In monomer it is not possible, because in both the sides you have, see, if you have a diacid, dicarboxylic acid, both the sides you have a 2 carboxylic acid, or dihydroxy compound, you have both the sides you have 2 hydroxy groups. So, they cannot, the monomers cannot cyclize intramolecularly, but cannot they cyclize at all? Yeah, they can in a oligomeric stage, because in the oligomeric stage they have 2 different functional group at both the sides. So, if you talk about reaction between dihydroxides and dihydroxy compounds, at the intermediate stages you have hydroxy acids or hydroxyamine, then they can intramolecularly react and cyclize. Okay. Let us see some example, generic example. So, if I have a BB type structure, this can cyclize to give like this. Even in case of AB type monomer also, you can also have cyclization at a intermediate step. Okay. So, these are showing the possibilities of cyclization. If you have AB type monomers, then in monomeric stage also it can intramolecularly cyclize. If you have A or BB type monomer, it can only cyclize at oligomer stage. Now, what is the tendency of a monomer to cyclize, participate in cyclization reaction compared to a linear reaction? Okay. If you have an intermediate molecule like this, it can take part a intramolecular cyclization reaction, or it can also, as usual what you just learn all the time, it can take out linear reactions to make high molecular polymers. Okay. Now, it is desirable for us, it is desirable that this take part in linear polymers, not in cyclization. If it forms cycles, then it will form low molecular weight, it will come out from the reaction, and those will contribute to the lower molecular fraction, and it will increase your polydispersity. And you cannot completely avoid the cyclic formation, they are always present in the cyclic formation. That is the reason why your polydispersity goes up little over 2, okay, because you cannot avoid completely formation of cyclics in a step polymerization, always present little amount. So, that is contributing to your PDI to be little over 2. Now, what is the comparison? If I compare cyclization process and the linear polymerization process, what are the tendencies? Now, if I compare between tendency versus linear polymerization. Tendency. Now, this depends upon both kinetic factor as well as thermodynamic factor. Thermodynamic factor comes from the stability of the ring size. Now, when they form cyclics, it is always forming a ring, and the size of the ring determine whether it will form. In thermodynamically, it will form, favor the formation or not. Now, you know from organic chemistry knowledge what is the stability of different ring, what is the strain. If I go from a ring size to 3 to 4, strain comes down, then 5 again strain comes down, 6 is the least. If I go up again from 7 member ring, again it goes up, 8 the strain goes up, and then again it starts up to 13 it goes up, and in ring strain, and after 13 it comes down in strain. So, if you have a ring stability order, then you have 3 membered ring, 4 membered ring is so if you talk about compare ring size, then 6, 14 and larger are the most stable rings, and then the 5 and ring size between 7 to 13, and the least stable is the 3 to 4 ring size. Now, this is applicable for methylene groups. Also it is ether, or the backbone, the cyclic ring has ether or other carboxylic groups, or carbonyl groups. Now, what we will discuss in the next class is take this forward, this ring size. We know that what is the thermodynamic factor. The ring size determines the stability and of course guide the tendency of your formation. We will talk about kinetic factor in next class, next lecture, and then compare quantitatively between what are the factors we should take care to reduce the cyclic formation, as desired that you should have minimum amount of cyclic in the polymer mixture, but as I said that you cannot avoid cyclic formation. So, that is the reason why you always get a PDI little over 2. Okay. So, we will come back and start with repeat this thermodynamic factor little bit, and then start the kinetic factor, and also talk about the reaction conditions which differs the cyclic formation, okay, which are responsible for cyclic formation. Okay. See you.